What's up, everybody? I'm live from Vancouver at NeurIPS. So Nikita gave us a great overview of like the how they created CoTracker. I just got a really short presentation more about how to use CoTracker. And it's glad that Nikita is here so that if there are some technical questions on using it, perhaps Nikita could jump in. So the kind of through line of this presentation is we're going to use CoTracker and apply it to a 51 data set. So just gauging the chat here. Those of you who have used 51 before, drop 51 in the chat for me. If you have not used 51 before, drop 50 in the chat. Just want to get an idea of you guys' experience with using 51. But essentially what I did was took CoTracker. I thought it was an awesome paper and really liked the work that Nikita had done. And I actually haven't used a point tracking model before. So this is my first time using a point tracking model. So I figured let's go ahead and give this a go and use it on a 51 data set. I'm going to share a link to this Google Colab immediately after I'm done talking. So don't worry, there will be a link to this Colab for you here, and you can run the code for yourself at home. So we start off as we typically do by installing 51 and then a couple other dependencies here, image.io and FFmpeg. These are what we need to parse our video and have CoTracker work. I'm going to pull a data set from Hugging Face using our integration with Hugging Face. The data set's actually right here. I didn't fill out the model card or anything, but we'll look at the data a little bit later. But there's 8 videos in this data set. So go ahead, parse it, load it into 51. And as Nikita mentioned, there's 2 modes of using CoTracker. There's the online mode and the offline mode. The online mode will process video sequentially in a sliding window manner, and it tracks points in a forward-only fashion. And offline is going to process the entire video at once using a single sliding window. And so this is great because we could do tracking of points bidirectionally. So we can use information from both past and future frames. As I understood from the paper, the offline version has better performance, especially when you're trying to track occluded points. So I've summarized the differences here in this short table. CoTracker does have an awesome repository that they shipped along with the model. But in this case, I'm just going to use the model from the Torch Hub and specifically the offline version of the model. And I've got a couple of utility functions here. I'm not going to go too in depth on these, but we're essentially this is a function that's going to read in a video and return a array. And then here's a video here. Sorry, a function here to show the video. So here's just an example of the type of video that we are going to run inference on. And once I convert this video to a tensor, we end up with a tensor of shape. The model actually will accept a tensor of shape BTCHW. So that's batch size, number of frames, input channels, height, and width. So in this case, this video right up here that we just looked at of the motorcycle rider, this is a batch size of 1 because it's 1 video. We're working on 62 frames with 3 channels, and this is the resolution. Go ahead and just move the model and the video both to the CUDA device. And an important parameter when using CoTracker is grid size. This essentially is just the number of grids that are going to be tracked in a video frame. And so when we have a grid size greater than 0, we are going to compute tracks for a grid of points based on the first frame. And the grid size is actually grid size times grid size. So if I have a grid size of 10, that's going to be 10 by 10, so 100 points that we'll be tracking. There's also a couple other parameters that you can use. There's the queries and segmentation, seg-m mask, which is meant to compute the points just on a segmentation if you wanted to do that. We're just going to stick with, we're not going to use queries or segmentation masks in this short little demo here. We're just going to use the entire video. So important thing to note here is that larger values of grid size is going to consume more GPU memory because this determines the number of points that the model needs to track. So more points being tracked means more GPU memory that is going to be used. So what's going to happen is CoTracker is going to use a grid of points that's going to be overlaid on the video frames, and then we'll track those from the first frame throughout. And it's quite easy to run inference. We get the predicted tracks, predicted visibility, and then we pass the video and the grid size to the model, and we get our output. And so the output here that we get, it looks something like this. So batch size of 1, 62, 402. And so specifically right now, we're looking at the predicted tracks tensor. So again, This is the batch size. This is the frames. So just the number of frames of the video, the number of points that we are computing. So in this case, we passed a grid size of 20. And so this is 400 because 20 times 20. And then the coordinates are just the XY coordinates of each tracked point in the frame. And these also have a visibility, which is takes on a value of 0 or 1 that kind of corresponds if that if that point is in the frame or not. There's also another tensor that we get out when we run inference on the model. This is the predictive visibility tensor, as I alluded to. This essentially is batch size, number of frames, and then 400, because 20 by 20. And we'll have 1 for visibility. So it's essentially just a binary indicator, so whether the point is visible in the frame or not. CoTracker does have a awesome suite of visualization tools that you can use to run all sorts of really cool visualizations with your predictions. And so to work with that, you just clone the repo, import the visualizer, and we can see this is what the tracked points look like. And so we're tracking based on the first frame, all the points that are present throughout. And yeah, important thing to note here is the camera is panning. So as the camera pans, you notice that none of these points over here, like by the gas station, were in the first frame, so they were not tracked. Whereas points on the motorcyclist jacket and pants and the actual motorcycle itself, those points do get tracked because they're still in the frame as the camera is panning. So what we're going to do now is run CoTracker on a FiftyOne data set. And I'll also link to this repo as well. I'll link to everything as soon as I'm done talking here, but I'm essentially just pulling some helper functions here to make life easy for us and not clutter up the notebook. And we're going to run inference using CoTracker on a FiftyOne data set. So something to talk about is like the workhorse, if you will, of this GitHub repo. So this function here, the function that creates key points for a batch. So the input is going to be the predicted tracks and the predicted visibility, as well as samples. And then for each sample, we normalize the coordinates. They're going to be normalized to 0, 1 range because that's how we need them to be in FiftyOne. And then for each frame in the video, we create a list of FiftyOne key point objects. So each key point object is essentially just a tracked point that is visible in the frame. The points attribute of the FiftyOne key points object is just a list with a single XY tuple. And then there's also index, which is the points index in the tracking sequence. And so what this function does here is it's going to then create a key points object for each frame in the video, like I mentioned. And we're going to add a field to the FiftyOne dataset with the name tracked key points. And essentially, it's just a field that contains the key point objects in each frame. So we're not going to use the confidence because, as I understand, the confidence is actually not provided by CoTracker, so I don't parse that into FiftyOne. And then there's also the label attribute, and we're not going to use it in this implementation, actually. And then there's also the visibility. And so to run inference on the whole data set, we're just going to import the main function. And so if we look at the GitHub repository here, we look at the utils, we're essentially running this main function here. And of course, I'll link to this code so you can go ahead and take a look at it. But essentially, we're just going to process each batch using the CoTracker model. We'll get the predicted tracks and visibility for all the frames in the batch. We'll create and add the key points, and then we'll update the FiftyOne data set with the key point information. And we're just going to do a couple of configurations here. This is just to loop the videos and color by instance of key point. And this looks a bit odd right now, but I'll go ahead and just open up one video here. Zoom out a little bit here. And so I do apologize. FiftyOne runs a bit slow in Colab, and that's just due to Colab itself. And in this case, I believe I used a grid size of 25. So we have 25 by 25 for a total of 625 points that are tracked. And you can see that we do this for each of the 8 videos. So let's just go ahead and go back to our motorcyclist that we had initially looked at. We looked at the motorcyclist and visualized it using the visualizer tool from CoTracker. But here, we're just parsing it into FiftyOne and using FiftyOne to visualize those key points. And you can see that we end up with essentially the same results as what we see in CoTracker, which is expected. A couple other examples. Here's some folks here that are walking and skating through a hallway, and you'll notice as the camera pans, the points up here were not tracked, and we still are tracking some of the points from the skater here. Another video that we have is this one. I thought this one was interesting because essentially we have somebody running a photo under a faucet, and you'll see how the points get tracked in this case. So I thought it was pretty cool because there's lots of movement happening here, and we're still able to track that picture quite well. So it's cool to see that. Another example is these folks here that are dancing. You can see here that as the camera pans out, the stuff that was not in the original first frame, we lose those tracks, but we do keep the rest of them. And this is probably one of my favorite ones here. You'll see we're able to track the snowboarder as she is tracking down. And even though there is some occlusion due to that cloud of snow, we're still able to track those points. So that is essentially running CoTracker on FiftyOne in a nutshell. I just want to close with a few kind of things that I've learned doing this project. So as I mentioned, this was the first point tracking model I've used, and I learned a lot about working with video data and how much GPU memory it ends up consuming. So the original images that I pulled were from a website called Pexels, and you could download videos from Pexels. And the original videos were fairly high quality, fairly high frame rate. And as you saw with the videos of the motorcyclists, they're quite nice, quite clear. And the nice thing was they were relatively small in file size. But when I convert a video that's relatively small in file size, for example, 5 megabytes or so, when you convert them into a PyTorch tensor, they actually end up taking up like several gigabytes of GPU memory. And of course, this was because the original videos had quite a high FPS count. A 5-second video running at 30 frames per second would be 150 frames. And then you couple that with each of the tensors that represent the outputs, the predicted tracks and predicted visibility. Those end up being several gigabytes as well. So to overcome this challenge of blowing up GPU memory, what I did was any video that was longer than 10 seconds, I downsampled them and reduced it to taking every third frame and then just reducing the frame rate to 7 frames per second. So this helped decrease the size of that tensor and still maintain some smooth playback. And as Nikita was mentioning, the offline mode does end up consuming a lot of GPU memory. I imagine that had I used the online version of the model, probably wouldn't have to have gone through this step. But again, these were like super high quality videos. They did far exceed 1,000 frames in total. I admit it might have been more reduction than necessary, but again, it allowed me to run inference on the whole data set. And in this case, I was using a A100, which has 48 gigs of RAM. And I was able to use a relatively large grid size of up to 50. So 50 times 50 for the number of points that are being tracked, and was able to maintain the GPU without blowing up memory. Overall, I was quite happy with those results. Although the online version was more memory efficient, when I ran the model, I just wasn't as happy with the results as I was with the offline version. I found the offline version just was able to track points a lot better. I guess a natural extension of this would be maybe doing a version 2 of this project, of this short little session where maybe we use segmentation masks, right? So maybe segment out the background and maybe just track the people, or pass in query points and see how that gets tracked throughout the video. I think that would be the logical kind of next step of this. One thing I could think of doing is maybe using some type of zero-shot segmentation model across all the videos, get the segmentation mask for the videos, and then just use that to track the objects of interest. But yeah, that was it from my end. I'll go ahead and I'll share the link out. It was cool playing around with CoTracker and parsing it into FiftyOne. It was definitely a fun learning experience for me and a good experience for me to test drive the functionality of key point tracking in FiftyOne.